In this video, we will try to find the Euclidean distance between the adjacent points for PAM signaling scheme. So, if we draw our PAM signals, we can draw it on the phi 1 axis as I explained in the video, and then we can suppose we take m equals to 4 and we apply this on m4. So we will have 4 signals. If you recall your signal points, so your signal points as I discussed earlier in my lecture, that your signal points are you can have with M4 we will have 4 signal points, right? 4 signal points on the phi axis can be expressed as A, M, eta sub P and AM, where AM our A sub M is plus minus 1 plus minus 3, because we have M4, so M minus 1 is plus minus 3. We can write it in this form, or we can write it in this form, this eta, sorry, let me write it, eta G over 2. We can also write it in this form as well, right? So we have the same AM. Now, if for M4 we want to find out these signal points, so our signal points, keep in mind the expression for your AM, right? Your AM is 2 times M minus 1 minus capital M. So you can always substitute M1, 2, 3, and you can find out the values of AM, right? Yes, we did in the previous lecture. So if I substitute these for M4, 1, 2, 3, 4, if I substitute this in AM, I'll get these values. I'll get these values, and with the basis function phi 1 of t, we can identify these points to be these 4 points. Let me specifically draw it here. So we can say our S1, S1, you can find, just substitute 1 here. So our S1 would be minus 1. We can get minus 1 from this expression. Our S1 would be minus 1 times EP. So I can write it here that this is minus 3, not minus 1, minus 3 times under root eta P, right? This is the point. If you want to write the this is because this is just x axis, so we have only x coordinate, right? And the other one would be 0. You can write these coordinates like this, minus 3p. Similarly, you can write the coordinates for this, for the other point, and I'll write it above this one, which is under root negative eta p and 0 for this one, for the point S2. This is my S2 point. Now I have another point S3. Put m equal to 3 and you will find this this point. So for m, for this m, in this expression m equal to 3, we can see that you have 6 minus 5, which is plus 1. So with a plus 1, we can find this coordinate AM is plus 1. So you can find the point over here. So you have plus eta p, and vertical axis is no vertical axis 0. Similarly, you can have another point here, which is 3 e eta p and 0. These are the 4 points. These are the 4 points. 4 points which we have written in terms of the pulse energy, the symbol energy. You can also write it in terms of Eg over 2. Just replace Ep by under root Ep by under root Eg over 2, and you can find out these 4 points. So you can locate these points. Now we are interested in the Euclidean distance between the adjacent symbols. Now just consider any you can take any two signals. Suppose this is my we will generalize it. Suppose this is my this one is Sm and this one is Sn. I am using the same notation as given in your book. Suppose these are the two adjacent points, Sm and Sn. This is Sn, this one is Sm, S sub m. So these 2 points, and we are interested in finding out the Euclidean distance between these 2 points, right? So the Euclidean distance between these 2 points. Well, let me show you how to find this Euclidean distance. But before finding out this distance, let me recall your previous knowledge. You are familiar with the Pythagoras theorem, right? So if you see a Pythagoras theorem, if you have this is x-axis and this is x-axis and this is the hypotenuse, right? I mentioned it, hypotenuse. This is the base and this one is perpendicular. So if you are interested in finding out the relationship, you are familiar with this relation. D square is equal to the square of the base square of the perpendicular, and you can find this distance d by taking the square root of the base square and the perpendicular square, right? Now this I'm just interested in this distance d with 2 points. Now it is base plus perpendicular, but if we have if we say that okay, our if this line, if this hypotenuse fall over this axis, if I say that okay, it falls over here, so no perpendicular. Now perpendicular is 0, but d is still there, right? D is still there. It falls over the x-axis. So it falls over the x-axis. This point becomes 0. Perpendicular, this is 0, right? Perpendicular is 0. So I can write, still I can use the same expression. I can say that okay, my d is now b square plus 0, no perpendicular, 0 square. So it is actually the square root of the square of the base, right? Now if you observe here this base, how do you find the base? It is actually these 2 points, right? These 2 points, the base is these 2 points because it is now on x-axis, and you can just find out the base if you have x1 for coordinates for this one and coordinates x2 and 0 coordinates for this one. You can find out the base to be x2 minus x1, right? You can use this one, or if you right, if you just want to take x1 first and x2, like if you can use this expression, or just put a mod over here. If you put a mod over here, you can just write x1 minus x2. So it results, so the result of this one and this one would become same. Negative sign would be ignored. So you just you can say that okay, the base, the length of the base is x2 minus x1 whole square, right? x2 minus x1, this is the base, and if I square it, I'll get this distance between these 2 points. If you put this mod here, you can take x1 minus x2 and it would also give you the same distance. Whether you take x1 first or x2 first. So this mod has a very good like it just the compensation for the sign. Whatever the point you take first, you will get the same answer. The distance will be positive. This distance will be positive. So it is x2 minus x1 whole is square. So we'll use this expression now to find out the we'll use this expression we'll use this expression to find out the Euclidean distance for our signals. Now going back to my signal points, if you see here we have Sm. Now we assume that we are taking our Sm is we are taking our Sm, which is actually this point, and Sn, which is actually this point. So we have these coordinates. In general, if you see the coordinate of Sm, if you generalize the coordinate of Sm, we can rewrite it. We can rewrite these coordinates, and let me rewrite it. These two adjacent points. Let me rewrite the coordinates of these 2 points. Right. So my Sm is actually Am and under root eta p, and my Sn, the other signal, is actually An under root eta p. These are the same points which I have just explained in the above diagram. So these are the same points. We want to find out the Euclidean distance. The Euclidean distance is which we mentioned, that the distance between point M and point N. This is actually the square root of the difference of these 2 points, Sm minus Sn, and we get the mod square. It's the same as the square of the base, as we discussed above. So because we have just a base now. Now put these values. Now substitute these Am. This is actually Am square root eta p minus An square root eta p. Now you can take any of these points. I'm just taking these 2, right? And I'll substitute it here. Now solve it. If you solve this one, what do you get? You can also this is common under root ep, so you can just take it out, this common thing, and you will have inside Am minus An square, and under root, we can write it under root ep square, right? Now if we observe this one now, Am minus An square and under root ep square, just simplify this, and we have an expression which is Am minus An mod. We put that mod, right? It's the same mod, and this square also cancels out, so you have only under root ep. So this is the Euclidean distance. This mod, keep this in mind. This is the mod. This one is the mod. So that you take 1 here, 1 as we have seen that our Am and An are 1 and 3, the points which we have considered, 1 and 3. So 1 minus 3 is minus 2. If you take mod, you will get 2, right? Similarly, if you take 3 here and 1 here, 3 minus 2 is 2, mod is 2. So you can take any of these values. So M and N can be generalized. When you take this mod, it doesn't, your magnitude is same. And then you have the energy of the pulse. You can also write it, you can just substitute this one. You can say this can also be written as Am minus N and Eg over 2. Right? You can also eta epsilon sub g over 2 if you use the energy of the gate pulse for band pass signals. Now as we already know that this is the adjacent points in pulse amplitude modulated signals differ by 2 units. So we already know that in PAM, the adjacent points, adjacent points, signal points, right? The adjacent signal points differ by two units, right? So keeping in mind this identity, that okay, that because we see that AM is plus minus 1 plus minus 3 plus minus 3 and so on up to M plus minus M minus 1. So if you see the adjacent points, they differ by 2 units. So keeping this in mind, we can say that okay, this AM minus N mod, this mod is actually equal to 2. So we this implies that our Euclidean distance is 2 times under root eta, peak energy of the pulse, or you can also write it in terms of EG. So you can also say that okay, it is equal to 2 times under root EG over 2, or you can say square root 2 times EG, right? So this is the same. I hope now what we can do, we can substitute this EG, this epsilon sub g, and we have already computed it in the expression above. So the Euclidean distance, if you substitute EG, let me write it specifically where we have taken this the pulse energy. We have derived an expression for the pulse energy, and if you see that one, the bit energy, we have derived this expression. The expression is, let me recall that expression before writing it. Let me recall that expression. So if you go back to your energy, the energy, we have this expression. We said that the energy is equal to m square minus 1 times E epsilon g6 log of m to the base 2. So we have already derived this expression. Now if we substitute this expression in the above equation, we can conclude that our energy actually equals to, let me substitute this, and we can say that okay, our energy is actually equal to we have to substitute it. This is for the average bit energy, and for EG, if you substitute this, we have to substitute for EG. So this will be equal to let's put it there, right? 2 times for EG, 2 times 6 log of m to the base 2 divided by m square minus 1. So m square minus 1 into EB average. So we can substitute this value to find out the minimum Euclidean distance, and this is now our expression for the Euclidean distance, log of m to the base 2 over m square minus 1, and this is the epsilon of this value. So if you observe your minimum Euclidean distance, we can write it in this form as well. Now in the special case, when m equals 2 or binary signals, the pulse amplitude modulated waveforms have the special property that and what is that special property? When you see that m equals 2, which is actually a special case, when you say m is equal to 2, then our signal, pulse amplitude modulated signal S1 of t is equal to minus S2 of t, right? And these two signals have the same energy, and cross correlation coefficient, if you see, these two have the same energy, right? And the cross correlation coefficient is -1 for these two, right? These signals, such signals are called antipodal signals. Antipodal signals. So the cross correlation coefficient is -1, and these are like the two signals, pulse amplitude modulated signals having same energy with opposite polarity. So this is also known as binary antipodal signaling scheme. Then we have M2. We also call it a binary signaling scheme, binary antipodal signaling scheme. So we also call it, let me write it specifically, we also call it the binary antipodal signaling scheme when our m is equal to 2. So this is all about the Euclidean distance of PM signaling scheme, and we will move to the phase modulation in the next lecture.